Another natural way to describe an exponential model is to choose a nice multiplier and then describe the amount of time it takes. Just to make things even more complicated, we might not know the starting value. We might know the value at some time after we start. For example, a scientist is culturing bacteria in a petri dish. Typically, when they start culturing the bacteria, they can't actually see what's in there. It's only after the culture's been going for a while that they can count the population. So they observe that the population doubles after every 2.3 hours. And at the 10-hour mark, there are 10,000 bacteria in the dish. So we're going to make this table just to help us think about this. At the 10-hour mark, there are 10,000 bacteria. At this point, the population has not doubled. And now the population is going to double every 2.3 hours. So if 2.3 hours pass, it's now been 12.3 hours. And we have 20,000 bacteria now. We've doubled once. Another 2.3 hours pass. It's now been 14.6 hours, and we've doubled twice. We've got 40,000 bacteria. After T hours then, how many times have we doubled? Well, we want to know how many times we've added 2.3 hours since the 10-hour mark. So first we take T minus 10. That's how long it's been since the 10-hour mark. And then we divide it by 2.3. And that 2.3 is how long it takes to double. So at 10 hours, of course, 10 minus 10 is 0, no matter what we divide it by. 12.3 minus 10 is 2.3. And when we take 2.3 divided by 2.3, we get 1. 14.6 minus 10, that's 4.6. And we divide that by 2.3, we get 2. Right, so how long since the 10-hour mark divided by how long it takes to double will tell us how many times we've doubled since the 10-hour mark. Our function, well, we'll say we start at 10,000. That's a known value. Times, we're going to be doubling. We'll multiply by 2. And then, well, how many times will we double? T minus 10 over 2.3 gives us how many times we double. And that's a function of t. It's a kind of unpleasant function, but it's a function that we've written down. And this gives us our general form of an exponential model. Here we have the most general form of an exponential model. And if you try to memorize this, you're going to get lost. So please remember the example we just saw and how we constructed this. So what do we have? We have some starting value of our input and some starting value of our output. The starting value of our output is what we multiply by at the beginning. The starting value of our input, we subtract it from whatever input we're using. right? So if we take f of x1, this will just be m to the 0, and we'll just get f1. And then after we subtract, we divide by this thing that's a triangle in front of x. This triangle is called a delta. We call this delta x. And it represents the change in x. That symbol delta is often used to represent change. It's the change in x that gives us the multiplier that we were given in our problem. So we will work with this really extensively, and after some practice you'll get used to it. It takes a little getting used to. But if you think through the model and think this exponent tells us how many times we multiply by m, that will help to keep track of where everything goes. Okay, things are not quite complicated enough, it turns out, because sometimes we aren't explicitly told what the multiplier is, but we can deal with that too. Okay, so we're back to the scientist culturing bacteria in a petri dish. After 5 hours, there are 3,000 bacteria. And after 12 hours, there are 30,000 bacteria. We're going to build an exponential model here. When 7 hours pass over here, the population is multiplied by, well, we take 30,000 and divide it by 3,000, which gives us 10. How did we find the 7? That was 12 minus 5. To find how much time has passed, we just subtract the times. To find out what we multiplied by, we divide. If the population's getting smaller, we'll get a fraction less than 1. If it's getting bigger, we'll get a number that's more than 1, either a whole number or a fraction. Okay, so all we had to do to find out the multiplier was to do that division. We'll say we start at time 5. We could theoretically pick either one of these, but we'll just pick the earlier time to be when we start. So our starting value of p is 3,000. Our multiplier is 10, and then our exponent is going to be the time minus our starting time is 5, divided by the time it took us to multiply by 10, which is 7. So time minus starting time divided by the time it took to get our multiplier. And there we go. The only thing different about this one was we had to do a little bit of division to find the multiplier.